Okay, so continuing on to section 12, 2 notes for statistics honors. In the previous section, we talked about confidence intervals, so now we're going to be talking about hypothesis testing when proportions are involved. This is going to be called a one-prop z-test in your calculators. All right, so might as well jump right into it. You guys are superstars at hypothesis testing now, doing both means and difference of means, so let's jump into it. This will look different, of course, because we no longer are dealing with mu and sigma, but rather just p, basically, in terms of the test. So let's just get into it. So again, you're basically testing the population proportion p. So instead of mu, we're dealing with p, which we'll show in the hypothesis in a second. So what are the assumptions? We need a simple random sample, and we need n times p naught, and n times 1 minus p naught are 5 or greater. Okay, so you won't be able to use the success failure thing anymore, which is one of the reasons why I did that box over here when we did intervals and I pointed to this, because now you're going to have to do this and this is greater than or equal to 5. And you might be asking, well, what is this p sub 0? Well, p sub 0 is essentially the value that the true proportion takes. So that's going to be p in our problem. So not p hat. Now here's where the problem exists, by the way, is because in each problem you're going to be given both p and p hat. So you're going to have to remember in a hypothesis test that you need to use the population proportion when you're checking the assumption. So be aware of that. Okay, next. The null and alternative hypothesis, they are the same but with different variables. So what was it before? It was mu is equal to mu naught. So now it's p is equal to p naught. Yes, it sounds like peanut. I say it all the time. But so what does that mean? Remember, this is just the value of proportion. So it's going to be p is equal to a number is going to be your null hypothesis. So the alternative is that p is either not equal to, less than, or greater than that same number. So it's not a big change. It's just the variable is different to signify that you're dealing with proportions. Again, we need alpha in order to make our decision. The test statistic is going to look different, but realize it's not that much different. Remember, for means, what was it? It was x bar minus mu divided by sigma divided by root n, right? So now we have our statistic, which is p hat, minus our parameter, which is p, over the standard deviation of the sampling distribution. Well, you learn that the standard deviation of the sampling distribution is that entire thing in the radical. Now, again, are we ready for more confusion? If you look at that denominator in the confidence interval formula, these were p hats. Now they are just p. Again, when you're given the problem, you are going to be given both variables p, which means you have to remember which p sub 0, or in other words, just p, your population proportion, to put down there when you're doing the statistics. So there are places here where lots of confusion can actually come from. Now, I think I pretty much summarized everything in here. Just remember this third one. We are going back to using the standard normal z distribution formula for this. So even though we use the t-table for intervals, because the z alpha over 2's are at the bottom of it, for this, we're going to be calculating p-values, which, yes, you could use the calculator for, but in order to calculate that p-value, you have to use the normal distribution table in terms of figuring that out. All right, let's go through an entire hypothesis test example to make sure you understand what you're going to be seeing. It says a survey claims that 9 out of 10 doctors recommend aspirin for their patients with headaches. To test this claim, a random sample of 200 doctors is obtained. Of these 200 doctors, 164 indicate they recommend aspirin. Is this claim accurate? Use alpha equal to 0.05. Okay, so this is a perfect example of a proportion problem. Note, there are no means anywhere. It's just a bunch of proportions that they're providing you. But you'll see that they actually gave you two different proportion scenarios. So just realize in this situation that you're always going to be given that. and that can be very confusing for people to understand. So first things first, assumptions. So our assumption is we need a random sample. So right in the beginning they said 200 doctors, so that's out. All right, so that's satisfied. So what else do we need? We need to do n times p is greater than or equal to 5, and n times 1 minus p is greater than or equal to 5. Now note, it's p, not p hat. So right now, we have to go back into our problem and designate what p is and what p hat is. So let's start. So it seems that it says a survey claims 9 out of 10 doctors recommend. So this isn't coming from a sample. This is coming from a prior survey, which means it seems that 9 out of 10, or 0.9, in our problem represents our proportion. So worth noting that is technically p sub 0, but we can just say p for now. Which means that if you look at this, it says of these 200 doctors, 164 indicate that they recommended aspirin. So they're saying that that's coming from the sample, which means 164 to 200 is our p hat, which by the way is 0.82. So right now we have a very important observation, and this is something that you can absolutely do at the beginning of your problem to make life go easier for you. I even recommend it. So that means for these, last time we would have used this. This time we're using this. So we're taking n in our problem, which is 200, and we are multiplying by 0.9 to get 180, which is greater than or equal to 5. And over here, we're doing 200 times 1 minus 0.9, which is equal to 20, which is also greater than or equal to 5. This can be confusing, because worth noting, because there are two n's as well, right? So you can see somebody possibly picking a 10 as n. So remember, n is always the sample size. So this value here is only for determining this, and that's it. We are dealing with the sample size whenever we're talking about any type of problem in a proportion problem. So these check out and we're good. But again, that is a confusing step now. It went from maybe easy in the interval stuff to, oh no, now I have to balance two variable p's and technically two n's, but normally they don't give you this number. They just say 90% was the claim. Just worth noting, but just throwing it out there. Okay, so if the assumptions are satisfied, we can go ahead and see our first proportion hypothesis test. So again, we need a null and alternative. The null is always a statement of equality. Our population parameter has changed from u to p. And now we're doing whatever the claim is. Well, p sub 0 is the claim, and it's that 90% of doctors recommend aspirin. For the other scenario, we're looking for the alternative, which is going to be the same values, but what's the sign? Well, it says, in this scenario, it says, the only thing it says is this claim accurate? So it doesn't say anything about less than or greater than, which means, again, we're going back into two-tailed world, which is p is not equal to 0.90, or 0.9 you can use. Okay, so what do we need? We need the test statistic. So if we go back here, our test statistic is right here. So we're going to do that. I'll write out the formula for the first time here. We're going to do z is equal to p hat minus p over p times 1 minus p over n. Now note, you can put p sub zeros if you want on all of these. It doesn't matter. I tend to just not, because it's just extra work. But just realize those three p's are different than this one. That's the key. So we go back and we go where our p hat is 0.82. We're subtracting our claim, which is 0.9. And then when we do the denominator, we're using the 0.9p as our value. Our n in this problem is 200. So we're going to get negative 3.77 as our test statistic. So remember, this is a z now. In the previous section, we did a very long, detailed look at t again. Now we're back to z in these problems. Okay, so we're back to our critical value and p-value approach. This is the original z tests. This is exactly the same concept. So the approaches do not change. Luckily, in this case, we don't need to worry about degrees of freedom because we're back in z world. So all we have to do is figure out what the p-value basically is. We could use the critical value approach, but and you all know how to do both. But just for argument's sake, let's take a peek at the p-value and see if we can figure out what this is going to be. So let's make a decision. Well, if you recall, our z is negative 3.77, so we're going to plot it on our graph. This is a two-tailed test. So we have this area, and we have the mirror area over here to deal with, which is technically 3.77. So we need to find this area. So what do? Well, there's two things we could do. We could look up negative 3.77 in our z table. So negative 3.77 is in our z table, which puts us right here at 0.0001. Okay, so that means our p-value is equal to 2 times 0.0001, which is 0.0002. Okay, that's pretty low p-value, right? So what is that going to mean? Since we're comparing that to our alpha in our problem, remember our alpha, if we go back, is 0.05. So we would say since this is less than 0.05, 0.0002 is less than alpha equal to 0.05. So we need to reject H naught. So when we do that, what would happen, we would claim, if we're rejecting H naught, that we would claim that the true proportion of doctors that recommend aspirin is not 90%. That is basically our change, and you know how to interpret that from the little things that we've done before. You just keep doing that. Now, another small thing here is, let's say you're using the calculator. So we're back to using normalCDF. So we would do 2 times normalCDF. We would go from, remember, use our original. So we would go from negative 1 E99 to negative 3.77. And then we would have to do mean and standard deviation of z, which is that guy. So that should give you the same exact amount when going through and doing the calculation, but I don't have that right here. But that's how you would calculate it, and you would get something around 0.0002, and then you can make your conclusion for the test. Whenever they do proportion tests, every once in a while they get a little tricky when it comes to it, just because proportions kind of lend towards that, and I'll explain that in this problem. For number 1, it says newborn babies are more likely to be boys than girls. A random sample found 13,173 boys were born among 25,000+ newborn children. Is this sample evidence that the birth of boys is more common than the birth of girls in the entire population? All right, so what is weird about this? So basically they said a random sample found 13,000+ boys out of 25,000 newborn children. So hopefully right away you go, oh, that's got to be my p-hat of boys that were born, right? So if you calculate that, by the way, it's around 0.517. Okay, but if you look at the rest of this problem, there are no other givens at all, numerically. So before we get into assumptions, let's just take a peek at what our null and alternative has to be for this. Okay, they're saying, it says, is the sample evidence that the birth of boys is more common than the birth of girls? Okay, so what would happen if the birth of boys is more common than the birth of girls? Well, our P represents the proportion of boys, as you know from this calculation. So what would happen if boys was more common than girls? Then P would be greater than 0.5. The proportion of boys would be more than 0.5. Therefore, the null would have been just that it is 0.5. Now, this is one of those that's very ambiguous, because technically the null hypothesis would be less than or equal to 0.5, but we don't do that. So the focus of our problem is going to be on this hypothesis when going through it. This does pop up a lot, so just be careful when you're going through and figuring that out. So we're dealing with the right-tailed test. So what do we need to do? We need some assumptions. So it looks like a random sample was taken, so random here, so that's good. we need to do n times p, n times 1 minus p. So what is n in our problem? It's 25,468. So I don't think we're going to have any issues here. What is our p? Well, again, remember our p in these scenarios is the population proportion. So we're multiplying by 0.5. So that is obviously, I don't even have to do that math. That is greater than or equal to 5 by a mile. And remember that this is actually the same exact number because you're multiplying by the same thing. So both of these are perfectly fine. Okay? So we're good with assumptions. Those check out. Oh, and I didn't mention this before, but worth noting that I might have said it in the beginning, but this right here is what ensures the normality of the problem. That is like the key. So the SRS is what it is, but if you want to ensure normality, then that's what this calculation actually shows. I might have left that out when I said it before, so now you have it since you obviously are going to look through all of this. Okay, so what do we do next? We do z. So what's z? It's going to be our p hat minus our p over our regular p, population parameter, times 1 minus p over n. Well, our n is enormous, 25,468. Okay, if we calculate this, we're going to get 5.43. So I'm going to just stick with p-value because I think it's much easier. So we're going to put 0.543 on our chart. This is a right-tailed test, so we only care about this area. Hopefully you know that if you look up 5.43 in the table, you are going to get an area of 1. Why? Because everything in the table is this way. So when you get 1 over here, you get approximately 1. You get approximately 0 over here. So our p-value is approximately 0. So again, on the calculator, you would do normal PDF. You don't do 2 times because there's no 2 tails. Of 5.43, 1E9901. Okay, you'll get a scientific notation value like E, and it'll be approximately 0, which means clearly we're going to reject H naught here. So what would be the logical conclusion? You basically would be booting this guy out, which means you would indeed claim that the birth of boys is more common than the birth of girls.